Do you really think that even if the finish line is 11 meters away and the tortoise gets a 10-meter head start, Achilles will still win? Why did you just suddenly change your answer from yes to no? Why did you do a full 180? Did a secret voice in your head tell you that? Or is it just because I inquired? Yeah, right. It's just because I said, do you really think that? But now, let's imagine. Wait, so you're telling me this is 4? This, in fact, is not 4. Now, I think I know exactly what you did. You searched up what is the sum of the series. Wikipedia told you Euler summed it to 1 over 4 using the Abel pseudo-summation, and then you said, oh, screw the 1 and the fraction sign. It's just 4. Anyone tell me what does the concept of infinity mean to them? No religious connotations, by the way, just mathematically. What does the concept of infinity mean to you? Anyone? Raise your hands. Oh, yes. Wait. Anyone? Oh. What does infinity mean to you mathematically?
Simply interface mean of infinite or infinity as an extent. If we add 1 plus 1 plus 1, if we add what 1.5 hour or infinite hour I get, then it never ends. And we can go get the result and it's very example.
100%. Of course. That's an absolutely, okay. That's an absolutely wonderful definition of infinity. For when you know something's never going to stop increasing, so it keeps increasing at this point. So then you can basically say that it approaches infinity. It's like a term for something that keeps increasing and never stops. In the same way, minus infinity is a term for something that keeps decreasing. So now, does that mean that if I add an infinite amount of numbers, it will always equal infinity? So imagine there's numbers in these little blanks. No subtraction, just addition. No negative numbers. Is this always equal to infinity for every conceivable number I put in there? And math professors, please don't spoil it. Is there any way to put numbers in here so that it doesn't equal infinity? Come on, raise your hands. Just stand up. Does everybody think that if we just add an infinite number that is always equal to infinity? No. I'm seeing lots of no's. All right. Now, usually I would ask you why no, but today I'm going to do that. So let's talk about actually why it is not. So let's start with something known as Zeno's paradox. So, does everyone know Achilles from Greek mythology? How do I draw? Oh, yeah. Okay. Does everybody know Achilles from Greek mythology? Yeah. So the guy who has a really vulnerable heel, right? Now, everyone knows that he runs really fast, right? All right. So if I run at like 3 meters per second, this guy has to be speeding at like 10 meters per second. And now we're going to look at a tortoise. Now, are tortoises particularly known for running fast? What do you think? Are tortoises known for running fast? All right, but be careful. The tortoise already won against the hare, right? You remember the tale of the hare and the tortoise. So maybe Achilles will end up in the same situation. But don't worry, today Achilles has drank his coffee, so he's not going to fall asleep. So the tortoise is now traveling in 1 meter per second. Well, that's still pretty fast for a tortoise, but I mean, maybe the tortoise also drank its coffee today. So the tortoise says, well, hey, that's not fair. I mean, you traveled 10 times faster than me, so can I at least have a 10-meter head start? And Achilles says, well, of course. What harm could it cause? So Achilles is right here, about to begin the race, and the tortoise is 10 meters ahead of him. So the tortoise already knows that it's going to win. So it's just putting on a poker face. So the fifth wins this race. Achilles, who travels 10 times faster, or the tortoise, who gets a 10-meter head start? Who wins? Louder? Okay, Achilles. Why? Louder. Let me pose you another question then. So, it's not just because he's faster than the tortoise. Alright, so the tortoise does it with a simulated model of Achilles. This is the tortoise. The tortoise is 10 meters in front of Achilles, but the finish line is only 15 meters in front of Achilles. So, wait a second. Oh, wait, no. It'd have to be really small, like 11 meters in front of Achilles. So, who wins? Do you really think that even if the finish line is 11 meters away and the tortoise gets a 10-meter head start, Achilles will still win? Why did you just suddenly change your answer from yes to no? Why did you do a full 180? Did a secret voice in your head tell you that? Or is it just because I inquired? Yeah, right, it's just because I said, do you really think that? But now, let's imagine what really happens. So if this is an 11-meter race, and the tortoise is 10 meters ahead, how much distance does Achilles have to cover? How much distance does the tortoise have to cover? Okay. How fast did the tortoise? 1 meter per second. And how fast is Achilles? Okay. So that means Achilles will take 1.1 seconds to finish from 11 over 10, but the tortoise will only take 1 second. So even though they kept their speeds, the tortoise still won in this race. So why would the tortoise lose in this race? It's not just the speed, even though that plays a part. The head start is not enough. Right. So, not enough. Now, let's try the same strategy. So, I don't want to clean the entire screen, so I'm just going to... Oh, I can't do that then. Okay. So, now... So, let's see. Achilles has how much of a distance to cover? How much distance does Achilles have to cover to finish the race? Louder? 100. Yes. So Achilles has to cover 100 meters, and how fast did we say he was? Okay. So how long would it take him to finish the race? All right. Now the tortoise gets a 10-meter head start, but the tortoise is only at 1 meter per second. So how So it takes him 90 seconds. Obviously, there's a huge lost this round, huh? Alright. You faced that. Want to see how I actually won? So, let's start from the beginning. The tortoise reasons. So, in order to surpass me, first you have to catch up to my head start, which was 10 meters away. And that would take you 1 second. Then, by that time, was moved by 1 meter. But then, by the time it took you to catch up to my second head, 1 second, I would have already moved 0.1 meters. So then, up to me, the next part, it will continue 1 second, and so on. But of course, 10, 1 plus 0.1 plus 0. You see the flaw in reasoning there, right? Okay, with the current kills here, who do you think really won? Who do you think won? Do you think Achilles stole the race? Yes or no? Achilles stole the race? So the tortoise won. This isn't looking too good here. Alright. So, for those of you who imagine the calculus before, what is the expansion of 1 over 9 on a calculus? Guys, he just entered it into a calculator. Etc. And this keeps going, right? Alright. And of course, if you want to, well, no, that's 1.11, etc. What is 10 over 9? Okay, good. I swear I heard one person shout 3.5, but I'm just gonna ignore that. Alright. It's not 1.111, etc. So, it really wouldn't take Achilles an infinite amount of time. The tortoise lied to us all, because the tortoise is still using 15th century math that he learned from the 3rd century Greek philosopher. Disappointing. So, that is the same thing. 1 plus 0.1 plus 0.01, etc. is equal to 10 over 9. So now, you can see the reasoning here on how an infinite amount of terms is exactly equal to infinity. Right? Now let's get to some more interesting ones, right? So you notice that this is decreasing over time. 1 is greater than 0.1, 0.1 is greater than 0.01, etc., and etc. Alright, so now let me give you another series where this keeps decreasing. 1 plus 1/2, this is 0.5. Plus 1/3, this is 0.33, etc. This is 1/4, this is 0.25. Plus 1/5, this is 0.2. Plus 1/6, this is 0.16, etc. So as you can see, would you agree that 1 is greater than 0.5? 0.5 is greater than 0.33? 0.33 is greater than 0.25. Yeah, so it keeps decreasing, right? Would you agree with that statement? Good. Alright. Now, tell me, if I add fractions like 1 plus 1 over 10 plus 1 over 100, etc. So if I keep adding these fractions the same way, increasing. Finite sum or keep increasing? How many people? I can't even raise my hands. How come? All right. How many of you think it's increasing? All right. A lot of you have raised hands for neither of them, which is kind of paradoxical. But actually, it does keep increasing. All right. Why it keeps increasing? So essentially, there's a nice. So we're going to start calling these sequences. So for example, A1 is 1, or 1 divided by 1. A2 is 1 divided by 2. A3 is 1 divided by 3. A4 is 1 divided by 4. You see the pattern here, right? All right. So then what is A of K, where K is just some random variable? Yes. 1 divided by K. So now, here's what I'm going to show you. So, let's say we have a function f of x. So this is equal to the sum from k equals 1 of a of k. Do you see where I'm going here, or should I explain? All right, let's explain it. So for example, if we take f of 1, that's just going to be equal to the sum from k equals 1 to 1 of a of k. That's just going to be equal to a of 1. F of 2 is going to be the sum from k equals 1 to 2 of a of k, which is a of 1 plus a of 2. Then f of n is going to be a1 plus a2 plus a3, etc. plus an. That's the reason behind it. Now, some of you more knowledgeable people in the audience, or some of you pedants, might say, well, what happens for decimal numbers? Because you can't have decimal parts of the sequence. Well, that's why we're going to use the floor of x. For those of you who don't know what that is, you can ignore it. For those of you who don't know it but you're interested, the floor of x is the less than x. So we always keep it an integer value. So for example, the floor of 1.5 is going to be 1. The floor of 2 is also going to be 1. The floor of 3 is going to be 2. The floor of 3.01 is going to be 3, so on and so forth. All right. So then, wait, what? Oh, okay. So now let's look at a graph of this. So actually, if we start from f of 1 exactly, then the floor of this would be 0. That's why, let me think. Yeah. We'll just count out f of 1. So then we'll start from f of 1 point, just a very small part above 1, etc. So then we would start over here at this part. Let me think actually. Is this the best way to go around this? I suppose it is. So let's see. So we have at 0, it's going to be 1. At 1, it's going to be 1.5. So I'm actually going to sift it around a little bit. So now you can think f of 0 is going to be the sum, So let's see. This is 1. This is 1.5. This is 1 plus 1/2 plus 1/3, so on and so forth. Looks like it's starting to flatten out over time, right? technically that is the case. But let me show you a similar situation. As the other person mentioned earlier when they were defining infinity, the sequence 1 plus 1 plus 1 plus 1 diverges, etc. So a of k is just going to be equal to 1. It doesn't even depend on k. So then the sum function is going to look like this. 1 plus 1 plus 1 plus 1 plus 1 plus 1, etc. And if you actually take these points on the graph and you connect them just like this, it will just have a constant slope upward. So we really don't want it to have a constant slope. We want its slope to always be decreasing and never approach a constant value. In other words, we want f prime prime of x to never approach 0. It should always be negative. So, an example of this is 1 plus 0.1 plus 0.01, etc. Now let's think about the slope over there. So the slope between the first 2 points is going to be 1 minus 0.1 over 1, which is 0.9. I don't think I need to put this 1 denominator in the future. So we just have 0.1 minus 0.01 is 0.09, etc. So now we can actually express this with the equation, the limit, as k approaches infinity, not 0, infinity, which essentially over time, of a of k over a of k minus 1 should some number n which is less than 1. Okay. So, why does this work? Well, essentially, think about it. If this approached something greater than 1, then it would keep accelerating and accelerating until it went up through the roof, like y equals x squared. That's unsustainable. That will just diverge. And now, some of you might be asking, why does it have to be less than 1? Why can't it be less than or equal to? That's probably the biggest question lingering in your mind. So now, think about this. This has a slope. Now this has a constant slope, right? A of k over a of k minus 1 is just 1 over 1. I think that's equal to 1, right? Wait, can I scroll? Oh no, I thought. So we can't use things like this, which means we can't have this slope approach anything that's greater than or equal to 1. So now let's test that out for the harmonic series. 1 plus a half plus a third, etc. AK is then equal to 1 over k. A of k minus 1 is going to be equal to 1 over k minus 1. Quite down. So then, limit k minus 1. Stand up and go. Louder. Yeah. Now, simplifying that even more, we're going to split it into k over k minus 1 over k, which is 1 minus 1 over k. Now, as k approaches infinity, or as k gets bigger, can someone please tell me what 1 over k approaches? Let's think about it in graphical form. So, this is the graph 1 over k, this is k, this is y equals 1 over k, so this is y. So as k gets bigger, what's happening to y? Louder? Yes. Y is approaching 0. But can 1 over anything actually be less than 0? Yes? Oh, wait. 1 over... Now? be less than 0? Alright, no, for good reason. So, okay, I guess we would put this, because you have to think about this side of the graph, is approaching 0 as k approaches infinity. Can't approach something lower than 0, can't go higher because it keeps decreasing, so that means this approaches 0 once you take the limit, which we had hiding over here the whole time. What in our rule, was it? Had to be some n less than 1. So, turns out this actually has a constant slope. Well, soon enough anyway. It's actually peculiarly growing like the ln function. So in fact, you can approximate the sum of the harmonic numbers as ln of x, the natural logarithm with base e for Euler's number, plus some constant. This turns out to be about 0.577, and it contains an integral that's off topic today, so we're not going to talk about it. So essentially, you should probably know that even though ln x slope keeps decreasing over time, never actually becomes 0. So those of you who have taken calculus will probably know that slope roughly corresponds to 1 over x, which means that as x gets bigger, it goes to 0, and never actually 0. It doesn't flatten out at some number. It just keeps going up and up and up. So now, and for those of you who have taken calculus 2, don't spoil it for the rest of us, we've already seen 1 plus 1/2 plus 1/3, etc. does not equal to an existent limit. Or rather, to be more accurate, the limit is x approaches infinity, 1 plus 1/2 plus 1/3 plus dot 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 plus 1 over x does not exist. Alright, so then please tell me what happens if we take the limit as x approaches infinity of 1 plus 1 over 2 squared, or 4, plus 1 over 3 squared, or 9, plus 1 over 4 squared, or 16, etc., plus 1 over x squared. Does that approach anything? Those of you who have taken calculus 2, please. Okay, for those of you who have not taken integral calculus, how many of you think this does not exist? Okay, that's 1, that's 2, no, that's 2. Oh, that's dad, isn't it? No, that's not. That's 3, that's 4. Okay, yeah, 4. How many of you think it does exist? Hands. That's 1, that's 2, 3, 4, 5, 6. Now please tell me none of those people raising hands took integral calculus. So, this actually does. Now, I was originally planning to cover this today, but I don't know if we have enough time for that and still get to the interesting part. So, I believe this is an extra. Actually, no. It's definitely factorization. Figure that out first. Of course, there were easier explanations using trigonometry, but this is not the core of what I want to get to today. So, those are some interesting convergent series. So now, let's talk about series that keep going up and up and up, or alternatively down and down and down, or there's a third alternative for series that just don't approach anything. What is it? What is the third alternative for a limit that doesn't exist? All right. What's the limit as x approaches infinity of sine x? Zero? I'm none. Anyone? Louder. Does it exist or not? Oh. Oh, come on. You're a math professor, aren't you? Or oh, okay. Math student. I think this is a general audience, so that would explain why the only answers I'm getting are coming from math majors. Okay. So, turns out this doesn't exist. But why? I thought that sine of x, if you draw it, it doesn't keep going up or going down. Its maximum value is 1, and its minimum value is -1. We're not talking about something like x sine x, where the amplitude keeps increasing over time until you just can't decide what it is anymore. We're talking about a plain bounded function. So if we have a bound on it, unlike something like y equals x squared, there's no top bound for it. We have a bound on this thing. So why doesn't the limit exist? No, you can't answer the same question in a row, by the way. Sorry. Why doesn't it exist if this function is completely bounded? Louder. Sorry? Okay. Why doesn't the limit exist if this function has a defined maximum and a defined minimum? Dr. Josie, do you have an idea? Dr. Roshan, do you have an idea? Yeah, he's still thinking. He'll never stop.
You know what? I can tell you this. If Professor Mathi can answer, we all will answer. He is the man with the tricks.
We're just passing it down the administration team. Okay, would you like to confer it to the next person in line? Okay. Seems like everyone except the math majors have collectively given up on this problem, and I am not letting the math majors answer today. So, the answer is, well, what is sine of infinity? It's not like well defined, because although it doesn't keep going up or going down, it keeps coursing through 1 and minus 1. It never stops going up or down in a repeating chain. So, it's not like we can eventually observe its amplitude getting smaller and smaller until it approaches 0. Or is it like goes up once and goes down once and then stops like that? Keeps going over and over, going through. So there's no end. I mean, this limit could be somewhere, anywhere between -1 and 1. But you get it? There's numbers within that range. We can't really define this limit because it keeps oscillating between -1 and 1. There are series, infinite series, that act in a similar. So, if we take that function and draw it, you know what it would look like? This. 1, -1, 1, -1, 1. Wait, -1, 1, -1. Hold up a second. Does this look a little bit familiar to you? So, does this converge on anything? Does sine x converge? So does this converge? The answer is no, by the way. Okay. No, it does not converge because it keeps coursing through 1, 0, 1, 0. It could be anywhere within that range by the time we get to infinity. It's an infinity number, but unfortunately it's not. So it's more of a concept or an idea. I guess every pedant and pedant will tell me that that's wrong. But that's my definition of infinity, a concept. But now we can essentially stretch the definition of what it means to sum. So there were lots of techniques that work spectacularly with sums, like, for example, Taylor series. Turns out, one infinite sums that do converge is that the mean of their partial sums is equal to the actual final sum, the final convergent sum. So that could be done with a very simple convergent series, like the one that we did before. However, this doesn't always have to diverge, even if the final sum does diverge. So there is no final sum for something like 1 minus 1 plus 1 minus 1, but the mean of partial sums does exist. So let's take a look for an example. So what's the partial sums? So it's going to be 1, 0, 1, 0, etc. Starting off. So then what is going to be their mean? Well, the mean of just this is going to be 1. The mean of 1 and 0 is going to be 2. The mean of 1, 0, and 1 is going to be 2 over 3. The mean of 1, 0, 1, 0 is going to be 1 over 2. The mean of this is going to be 3 over 5. The mean of the next one is going to be 1 over 2. You can see this keep lessening and lessening and lessening, so eventually it approaches 1/2. Okay? The mean, the final sum is equivalent to the mean of the partial sums. So now, this method of summation basically saying, well, if we can do that, the mean of the partial sum will be a final sum. So even though this doesn't actually sum to anything, the mean of its equal to final convergent sum for actual convergent series is 1/2. So we can say that the sum of half. Now, the summation is called Cesaro summation. There's an accent somewhere over here, but I forgot where it is. But now, let's talk about a more powerful kind of summation. So let's talk about minus 2 plus 3 minus 4 plus 5 minus 6 plus 7. Anyone? Dr. Rosan? Got an idea? Louder. Wait, so you're telling me this is 4? This, in fact, is not 4. Now, I think I know exactly what you did. You searched up what is the sum of the series. Wikipedia told you Euler summed it to 1 over 4 using the Abel pseudo-summation. And then you said, oh, screw the 1 and the fraction sign. It's just 4. I don't know how that happened. But that's my best guess. Alright, this should be pretty simple, not that hard. Start with 1, go to minus 2, then go to 3, which actually gives you, 2. Then you go to minus 4, then you go to 5, then you go to minus 6, then you go to 7, etc. Keep spiraling out of control, just like the function x sine x. There's no minimum bound. Now, let's try that earlier technique, the mean of the partial sums. So the partial sums, as you can see, go to be 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4, and so on and so forth. So, let's see what the means are. So the mean of this one is just 1. The mean of these two is going to be 0. The mean of these 3 is going to be 2 over 3. The mean of these 4 is going to be 0. The mean of these 5 will be 3 over 5, etc. So essentially, what it's giving me is 1, 0. 2 over 3, 0. 3 over 5, 0. And no, this half part does not keep going down to 0. It ends up eventually looking like this. So that mean of partial sum is not going to work in this. So what does? Series. Now, I don't think we have time today to explain why Taylor series work. Now, in fact, that professor at Brown University that I mentioned earlier spent that entire 1-hour session explaining why Taylor series work. But these series are essentially a way to, like for example, a trigonometric function, a logarithmic function, exponential function, the function counts how many people are laughing at any given time, etc. So, for example, the general formula centered at 0 for you parents up there is going to be f of 0 plus x of 0 divided by 1 factorial, this is divided by 0 factorial, plus x to the 2 f double prime of 0 over 2 factorial, plus x to the 3 over 3 factorial times f triple prime of 0, and so this is equal to the original function. Eventually, this is an infinite series. So then, let's try making that infinite series 1 minus 2 plus 3 minus 4 plus 5 minus 6, etc. So now, what do we need in order to do that? Well, first of all, it looks like every time we take a derivative, the function needs to alternate. So, for example, what can do that? Let's say we have x to the minus 1. Taking the derivative would give us minus 1x. Again, would give us 2x. Because we need it to be going up as the natural numbers in order, then that means we need this term to be 1 factorial over 0 factorial. Well, right. So this is 2 factorial over 1 factorial. This is 3 factorial over 2 factorial. So that it matches with these things over here. So, as you can see, this already gives us 1 factorial. This gives us 2 factorial. 3 factorial. So we're geared up and ready, right? Well, one more thing we have to do. I believe that doing it like this will give us 0 minus 1 plus 2 minus 2, etc. That's not what we want. Why? Well, let me show you something very bad that will happen if we do that, all right? So that's essentially, you might say, well, why don't we just take the negative to get what we were desiring, right? Well, turns out doing algebraic manipulations with these kinds of pseudo-sums is very dangerous. So for example, let me clear the board again, I guess. Let's try summing up that series from earlier in a little bit of a different way. Let's say that now we do 1 minus 1 plus 1. No, 1 minus 1, parenthesis, plus 1 minus 1, parenthesis, plus 1 parenthesis, plus 1 minus 1, parenthesis. Wait a second. 0 plus 0 plus 0 plus 0? Not like we can even odd. So, for all we know, exactly what named after Barry want to do algebraic manipulations like this. Oh, you can write with the back? That's weird. All right. So let's then just get on with it. The right series is 1 over 1 plus x squared, or 1 plus x to the minus 2. So let's start taking the derivatives of this function, just to get a feel for it. So f of x is equal to 1 plus x to the minus 2. Prime is going to be minus 2, 1 plus to the, minus 3. Double prime is going to give us 6 times 1 plus x to the minus 4. F triple prime is going to be minus 24 times 1 plus x to the minus 5. And what happens if we're trying to take f0 f double prime, etc. What happens when we set x to 0? This becomes 1, this becomes minus 2, 6, this becomes minus 4, etc. So now, let's try plugging that in. F of x is equal to 1 divided by 0 factorial plus minus 2 divided by 1 factorial times x plus a 6 over 2 factorial times x squared plus minus 24 over 3 factorial times x cubed, so on and so forth. What does that give us? 1 minus 2x plus 6x squared minus 24x cubed, etc. And now, oh wait, no, I forgot to divide. 1 minus 2x plus 3x squared minus 4x cubed, etc. And now, what value of x do we need to plug in order to make this? What value of x? Anyone figure it out? Dr. Roshan, you have an idea what's going on? 1 over 2? I don't know. Anyway, that's a great answer, thank you, but the answer is 1. Cool down. Alright, so now what happens if we plug 1 to the expression we use for the Taylor expansion in the first place? What is 1 over 1 plus 1 squared? Dr. Roshan, you are permitted to use the calculator. Anyone? Does anyone know what 1 plus 1 squared is? Am I lecturing to a silent audience? What am I hearing in the back? Can someone translate for me? 1 over 1 over